we call symmetry about the face. And I will try to explain how to recover the we call symmetry from the given topological face. So for this talk, I will briefly discuss three parts of the work. The first one is just some bigger picture about the topological face, especially about the 2D topological face. And for the second part, I will introduce the lattice model for the 3D topological model, especially for the bottom down model and for the streaming model. And for the third part, I will try to explain how to reconstruct the Hopf algebra from the given multifusion trinity. And since the Levin-Wen trinity is a special case of the multifusion trinity model, so for this case, we can also recover the Hopf symmetry for the Levin-Wen trinity model. And for the last part, I will discuss some open problems. And let me first remind some of the basic definition about the topologically ordered faces. The annual model has been studied for a long time, and usually the annual model is considered considering about the 2D system, because we know that there is some excitation, polycyclic excitations, and these excitations have their topological chart, and they have their fusion and split rule and the mutual statistic and so on. So we know that physically, from a physical perspective, the annual system usually there exhibit some kind of order called the topological order. That means that this kind of order is beyond the Ginsburg-Landau spontaneous symmetry breaking theory. That means that we cannot use the group theory to describe this kind of topological order. But we know that for this kind of case, we can use a quantum symmetry, quantum group to describe the phase transition between different topological faces. And some other physical property of the topological ordered faces is that there is some topologically protected quantum state degeneracy. It means that for a given system, if we fix for the given system with different topology, then the ground state is different. And this ground state degeneracy depends on the topology of the special manifold. And there is also some other tools that we can use to just detect the topological order. For example, we can use the topological entanglement entropy. We know that for a given topological system, if we try to calculate the entanglement entropy, it means that we will try to calculate the entanglement entropy, then we'll find that the topological entanglement entropy depends on the macroscopic property of the annual model. Actually, it depends on the quantum dimension of the topological phase, the global quantum dimension of the topological phase. And basically, there is also some crucial things about the fractional charge and fractional statistics. And there is also a crucial topic that we will cover in this talk is that there is age physics. We know that the holographic principle is crucial for physics. We know that there is many different kind of holographic phenomena like the ADS-CMT and the ADS-CMT correspondence. And for this topological phase, we know that there is also some this kind of duality. It means that we have a bulk theory and we have a boundary theory. Then we can recover the bulk from the boundary by taking the trivial center. And we can also obtain the boundary theory by doing the annual combination from the bulk theory. And so we know that for the topologically ordered phases, the ground state has the long range entanglement. And it has been shown that for the 1D gap system, there is no topological ordered phases. So if we just do not introduce any symmetry, and for 2D, we have a very good understanding of the topological phase. And for the higher dimensional case, it's not fully understood, and there is some higher dimensional excitation. And so the mathematical structure behind this model is not so clear at this stage. And now we have, since I have mentioned about the symmetry, so this symmetry is the crucial topic in the physics. And if we introduce the symmetry, then there is some richer structure for this topological phase. We know that we have such kind of table, like depending on the physical system, if we can say that if there is any symmetry or there is no symmetry, and if there is topological order or no topological order. If we know that if there is no topological order and no symmetry, this is a trivial phase. And if there is just a topological order but no symmetry, This is what we are talking about. It's just a topological order. And if there is some symmetry, this symmetry will introduce some point-like effect or point-like excitations. These excitations can also be regarded as some topologically protected excitation. So for this case, we'll have the SPT phase. And if there is also some topological order and there is some symmetry, and this symmetry introduce some extra excitation, we will call this kind of phase as the SET phase. And for the SET phase, if we just break all the symmetry, they will find that there is no topological order. So this kind of phase has a lot of examples like the Holden chain and the topological insulator. For the SET phase, we know that the fraction of polyphony effect is a typical example of the SET phase because there is the U1 symmetry. And if we just forget about this U1 symmetry, then we can also say that the fraction of polyphony effect is a topological order phases. And for the SET phase and the SET phase, we know that the topological, as what I mentioned, that for the 1D gap system, there is no topologically ordered phase. But if we introduce a symmetry, this kind of topological phases can even exist for the 1D system. And for the SPT and the SPT phases, we know that the state is easy to construct, but the lattice model is very hard to construct. Okay, so the above is just some physical background about the topological order phase. So from the mathematical point of view, we know that for 2D topological phases, now we have a very good understanding of the mathematical theory. It's just characterized by the unitary modular tensor category. And we know that the topological chart is characterized by the simple object of this category. And there is some fusion. The fusion and split channels that live in the Hopf space of this category. And there is also some braiding structure that's characterized the fractional statistics of this topological charts. And there is also the topological spin and some other structures. And for the SPT and the SET phases, it's more complicated. And we know that for the SPT and the SET phases, they are characterized by some more complicated mathematical structures. If we introduce some symmetries, there are two equivalent ways to describe this SPT or SET phases. The first one is just the modular extension theory. Modular extension of the UMTC. In this theory, we have a symmetry. We have a symmetry group, rep G, and we know that the rep G is a category. We are trying to do we have original UMTC, and we need to use the rep G and this UMTC to construct a bigger modular tensor category. This modular tensor category can be used to describe the SET or SET phases. And another way is that we use a J-cross modular tensor category. This is more intuitive because we know that if we have some symmetry, then we can introduce some excited polyparticles that have some symmetry charts that is labeled by this symmetry. Then we can put everything together. We'll find that there is some cross structure of this category. This is just a J-cross modular tensor category, and we can show that after some gauge process, they are related with each other. And another one is just the annual condensation theory. Now, annual condensation theory consider how can we just obtain one topological phase from another one. It's characterized mathematically by the condensable algebra or Lagrange algebra. And they will consider a given phase. They will just condense some anyons, and they will obtain a new anyon theory. And another one is the boundary bound geometry. Since boundary bound geometry, as what I have mentioned, is that the boundary theory for a given dark theory, there is several kinds of boundary theory. And actually, there are finite different types of boundary theory. But for a boundary theory, if we will try to find the corresponding bound, we'll find that there is a unique bound theory for this boundary theory. So this is a topological. This is sometimes called the topological holographical principle. And to make to clarify some notions, we will just illustrate some this kind of terms like the gapped phase and capitalist phase. So for the gapped phase, we just we will focus on the gapped phase. Because there is also capitalist phase. Capitalist phase is more complicated. And for this, we'll also consider chiral and non-chiral phase. Mathematically, the chiral means that the non-chiral phase means that there exists some unitary fusion category such that our topological phase is just the trivial center of this given unitary fusion category. And there is another notion called the non-free. The non-free topological phase means that we have in this ND anomaly-free topological phase is just a topological phase that has a lattice model in this dimension, which means that for ND topological phase, for ND anomaly-free topological phase, we have ND lattice realization of this topological phase. So for this talk, I will just focus on the gap, the anomaly-free non-chiral topological order, which means that it's the topological phase is described by some by the center of some given unitary fusion category. So now to discuss the lattice model of the 3D topological phase, I will first introduce some bigger picture. So the first definition is what is the rigorous definition of this gap. So we know that for the finite system, it's always gap, because we know that for the finite system, free system, because it's a finite metric, n by n metric, then we'll find that the first excited state and the ground state, there is always a gap, finite gap. But then if we just take the thermodynamic limits, we'll consider what is the gap, what is the gapless. The gap means that in the thermodynamic limits, there is always a finite gap between the ground state and the first excited state. This is the physical definition of the gap. And for the gap phase, why we just talk about the topological order usually in the gap plotting system? Because for the gap phase, we have a good understanding of the what does this mean by the Hamiltonian theory for the gap phase? Because we can define equivalence relation between different Hamiltonians. This is classified in the following way. And it means that two Hamiltonians, H0 and H1, are called equivalent if we can find a continuous path H lambda. This H lambda can connect this H0 and H1 and without closing the energy gap, which means that between from A0 to 1, we'll find that this H lambda always have a gap. There is no gap. The gap is not closed by this closed path. This is advective path. And if two Hamiltonians are connected by this advective path, we'll say that they are equivalent to each other. So with this definition, we can have a Hamiltonian theory of the topological phase. The topological phase at the Hamiltonian level is just a class of local gap Hamiltonian. So gap, I have introduced the definition of the gap. And the local means that for this Hamiltonian is a sum over some local terms. These local terms only act on the local region of a given spatial manifold. And this class of Hamiltonian realize some TKFT. So this is the Hamiltonian theory of the topological phase. And for the ground state, there is also a typical property usually called the long range intended state. It means that for the topological ordered phase, its ground state usually has a long range intended. So there are two typical models for this 3D topological phase. The first one is just the string model, which is a topic I will explain later in this talk. And the second one is a quantum double model. And we have a big picture about these two models. And we know that for the finite group, these two models are connected with a Fourier transformation, which means that we can map one to another one. They are equivalent, and their macroscopic theory are equivalent, and we can find some unitary transformation to relate these two models. And for the string model, we know that the input for the Levin string model, we know that the input is usually a unitary fusion category. And for the quantum double model, so in this case, we know that a unitary fusion category is for any unitary fusion category, there always exists a connected Hopf algebra, such that we can realize this such that the representative category of this Hopf algebra is this UFC. So So in this sense, we know that the streaming with the input data UFC is just equivalent to the column down model with the input connected with Hopf algebra. But generally, we can take the input data of the column down model as a general with Hopf algebra. In this case, we'll find that the streaming model is just the input data of the streaming model must be the multifusion category. So this is the basic motivation for us to study the multifusion streaming model. And we know that two lattice model realizes the same topological phase, we'll call them the Morita equivalent models for this topological phase. And there is also some duality between different models. This duality is just related by the local equivalence. At the state level, we know that the two topological states belongs to the same phase if they are related with some local unitary. By local unitary, we mean that finite the quantum circuit with finite depths, and for each layer there is some local structure, and there is also some EM duality, and so before I just discuss about how to find so now the main motivation for us is to understand how to find the Hopf symmetry for this lattice models. So the first step we have tried to do this is that we try to just construct the Hopf bottom-down model. So before we just discuss the bottom-down model, let us first introduce the notion of the Hopf algebra. To define the Hopf algebra, we first need to define the weak by algebra. Here we just give a definition for arbitrary given braided fusion category. In this arbitrary braided fusion category, a weak by algebra is just an object in this category. It is equipped with two structures. The first structure is an algebra structure. This algebra structure, there are two morphisms. One is mu. Mu is just the product morphism from W tensor W to W. And there is another morphism called eta. This is a unit morphism. It's just from the tensor unit to the W. And there is also a co-algebra structure. This is just the mu. Oh, sorry. There is some type of this is delta, and this is epsilon. For this delta, it's just maps W to W tensor product W. And for the epsilon, it's just maps from W to the tensor unit. And if we just use a string diagram, we'll find that to construct this weak by algebra, the axiom it can be constructed in this way. The first just means that the compatibility. This is the compatibility. This means that this is a product. This is a co-product, and they are compatible with each other. This is the compatibility of the unit and the co-multiplication. And the third one is just the compatibility between the multiplication and the co-unit. And for a weak Hopf algebra, we need to introduce another structure called the antipode. The antipode is just a map. In this category setting, the antipode is just a map from the W to W, and it satisfies these three conditions. And actually, there are some other conditions, and we can show that they are equivalent to these three conditions. And now in this talk, if we want to construct a weak quantum down model, it's a quantum mechanics model. So we need to take the category as the vector space. They will find that this is just the matches well with the Euro definition of the complex weak Hopf algebra. For weak Hopf algebra, there is two crucial morphisms. The first one is called the left co-unit. Left co-unit morphism. It defines in this way. And for another one is just the epsilon r. It's also they are symmetric with each other. And these two algebras plays a crucial role in the weak Hopf algebras. And we'll find that for these axioms, if we just f this s on the right hand side, we will find that there is some epsilon r. And if we just take it in left hand side, there is just the epsilon r in this right hand side of the equation. So now let us introduce another notion. We know that for the quantum double model, we need to have a quantum double structure for a given quantum group. Originally, this quantum double model is constructed from finite group, and the input data is just the quantum double of this finite group. And we can generalize this can be generalized to the Hopf case. To construct the Hopf quantum double the Hopf algebra, we need first to construct the ideal G. This G is constructed in this way because that we must ensure that the following definition is well defined. So we need to just take the dual. This W hat is just the dual of this W, and we further just constantly this G will have the well-defined structure of this quantum double. And so this is a little bit complicated, so I will skip this part. I will just explain how to construct the Hopf quantum double model. We know that for the finite group, this local operator is constructed in the following way. This AV is just the vertex operator. We just act on this G according to this direction of the each H. And for this BP, we do this kind of operations. Actually, we can reinterpret this as a special element of this quantum doubles. Actually, this is called the Hopf integral. Hopf integral is an element such that it satisfies these conditions. We know that L is called left-hand integral if for arbitrary x multiply with the L, or find that it's just the epsilon L with x times L. And if we just if integral is two-sided integral and satisfy the normalization condition, we'll call it Hopf integral. This is the special element we are trying to use. And why this element is crucial? Because we know that for this AV, we will see that this G, well, this expression is just a Hopf integral. We can put the Hopf integral into this AV, and we take the co-multiplication of each component. We'll find that for the finite group, the co-multiplication is just a delta G is just a G tensor product G. So it matches well with the finite group case. And for the Hopf quantum double model, we use this Hopf integral to construct the vertical algebra and the phase algebra. And we use because for each H, for the given lattice, for each H we put the Hopf algebra W. And we know that this W is W left module. This left actions, there are two left actions. The first one is the regular action or from the left hand side. The second one is from the right hand side. We can use the F to transform it into a left action. And there is also a W2 action over this W. This is introduced by this regular notation. This phi is just from the W2. And we just take this action as the following way. And in the following way, we can have two left module structure for all the W. So using this, we can just construct a vertex operator. This vertex operator, there is a special element. This H is just the Hopf integral of the W. So we just take the co-multiplication. Here I have omitted some symbol for the regular notation. And then we just take the co-multiplication of this element and put this in each H. Then we have a corresponding operator. This operator acts on a vertex. And this is just like the right hand side. And for this phase operator, we have a very similar construction. And for each phase, we will just take the co-multiplication of this phase. And there is a very crucial property for this construction. We know that for the pairing between this between this phi and this Hopf algebra, the element of this Hopf algebra, we will see that actually this can be written as for the phi, this can be written as a phi over the x1 test product x1 multiply x2, x3, x4, and then we act with a phi action. So this is the basic construction of the we call quantum double model. So what is the excitation of this model? The excitation model can show that actually we can show that we can use we can construct the corresponding Riegel operator to show that the topological excitation of this model is just given by the representation category with the quantum double. This is neutral modular tensor category if we take W as an irreducible, indecomposable, we call the algebra. And here we are trying to introduce two crucial notions. We know that for the lattice gauge theory, for the quantum double group with input as a finite group, this finite group is usually called a gauge symmetry. And charge symmetry is just what is a charge symmetry? By charge symmetry, we mean that this is a quantum symmetry such that the charge is just a representation of the symmetry. This is what this is the meaning of the charge symmetry. So for the quantum double model, we know that this W is a weak Hopf algebra, and it plays a role as the gauge symmetry, and the DW is just the Hopf charge symmetry. This is a general. Actually, this is a general the phenomenon. For a feature given non-chiral topological space, we can find the gauge symmetry, and we can find the charge symmetry, and they're related not simply by the quantum double, but we know that the charge symmetry and the Hopf symmetry are not unique. Because we know that for the DW, this is the quantum double. Its representative category may equivalent to another category. This category has the quantum symmetry that is not DW. So they are just unique up to the categorical Morita equivalence. And so the ring operator can construct it to create the topological excitation, which means that we have the ground state and we construct the ring operators. And to end of these ribbons, there are topological excitations. And another thing that we can consider about the gap boundary theory of this we call quantum double model. The gap boundary model is a 1D phase. This 1D phase is characterized by a W comodular algebra. I did not write it here, but we can say that we can regard the gauge symmetry of this 1D gap boundary as a W comodular algebra. And its excitation, its charge symmetry should also be a Hopf algebra, because we know that for the 1D gap boundary, its phase is just an interfusion category. So there is also a Hopf symmetry, Hopf algebra that its representation is just this 1D gap phase, 1D gap boundary phase. And there for the general Hopf case, we have not found a clear relation between the 1D gap gauge symmetry and the 1D gap boundary charge symmetry. And for the Hopf algebra, we know that they are related with the smart product because there is some very clear relation between them. And the boundary phase is, if we just denote the boundary phase as the B, then we know that from the boundary bulk duality, we know that the bulk theory is just the different center of this boundary theory. And this can mathematically prove that the representative category of the quantum double of the Hopf algebra is also equivalent to the different center of this boundary phase. They are equivalent as a braided tensor category. So there is a natural question about what is the connection between, because we know that for the finite group case, the input data is the finite group, then it's equivalent to the string model with UFC as input interference category as a representation category of this finite group. So we can naturally ask what is the relation between this we call quantum double model with the string model. And we guess that this is equivalent to the string model with the input as a rep W. But we know that for the rep W, for a given we call algebra, its representative category is usually a unitary multifusion category, not a fusion category. So in this case, we need to consider the multifusion string model. So for the multifusion string model, we have to discuss this model. We first introduce the definition of the string. By the string, we mean trivalent lattice, trivalent direct oriented lattice. This is called string. And the input data is just the unitary multifusion category. And its topological excitation is given by the different center of this unitary multifusion category. And it can be shown that this different center is also unitary multifusion category. Even for the unitary multifusion category D, its different center is still unitary multifusion category. It's not a multifusion category. It's still a fusion category. So for this vertex to construct the trinate model, we need to introduce the vertex space for this given trinate. We know that there is several vertices, and for each vertices, we introduce a space. This is just a fusion space. There are two types of the fusion space depending on the direction of the edge. There may be the first one or the second one, and we introduce a coefficient or a local normalization factor. This YCV. It's a factor, and we can simply choose it as this dB over this DC, and for to construct the trinate ground state, we first introduce three basic moves. This is very simple, like the fusion case, and we know that for the multi-fusion case, the main difference is that the simple the tensor unit is not simple, and there is the fusion structure there for the fusion A and B. It must there is some gradient structure. If this A is in the xij in the dij component, this B is in the gk component. They can fuse with each other and output some object. But if they do not satisfy this relation, there is no such kind of structure. So the main difference is that we need to introduce some gradient structure for these local moves. And the first one is that we can remove the loop. The second one is just we can just transform these parallel strings into the right hand side. And the last one is just the F loop. And we know that it's well known that these three local moves are equivalent to the pattern moves. And now the input data for this multi-fusion trinate is still the irreducible objects of this multi-fusion category. And the fusion rule is also here. But we know that this fusion rule there is also gradient structure, because we know that depending on the A and B in which component of this ED, there is some gradient structure between them. And the local normalization factor is some factor we can choose freely. It satisfies some consistency relations, and here we just fix it as a fixed number. A fully labeled trinate is just like this. We can for each edge we have a direction, and we can reverse this direction by just taking the dual of this object of the original labeled T, and we take the dual, then we can reverse the direction of each edge. And for the vacant edge, we just introduce this one tensor unit, and this I just label the component of this tensor unit. We know that for the tensor unit, for a given tensor unit, if we just try to fusion this tensor unit with another object, this object must be in some given component of the multi-fusion category. So there is just some corresponding component of this yi that can fuse with this simple object. It cannot be fuse arbitrarily, because there is some gradient structure for the multi-fusion category. And for the vertex, we just label the vertex with the morphism in this space, in this fusion space. This is completely the same as the Levin-Wen model. And this is what I have stressed about the multifusion structure. For the multifusion structure, we show that there is a gradient structure between this different components. If an object xij is in the dij component, it can only fuse with the component, the object that in the ygk. This means that this y is in the gk component, dgk component. It cannot be fused arbitrarily. If this g is not equal to, if this y is just in the LT, and if this L is not equal to the G, the fusion is just zero. So this is the basic part of this multifusion category. And for the typical example is just the weak Hopf algebra. And what I have to say that the basic motivation for us to study this is just we're trying to understand the weak Hopf, the trinate model corresponding to a weak Hopf polynomial model. And the trinate ground state can construct very similarly like the Levin-Wen model. For given a fully labeled trinate configuration, we just do the evaluation. After the evaluation, this is just a number. This number is just a coefficient for this configuration. Then we can take the sum over all the configurations. They will obtain topological state. This is the ground state of the multifusion streaming model. And to construct the boundary, to construct the vertex operator and the phase operator, they are totally the same as the Levin streaming model. For the vertex operator, we take the projection onto the space that they can fuse, which means that if this CAB channel is not zero vector space, then we take this space. And if there are zero vector space, we take the projection. And for this phase operator, we first introduce the phase operator that labeled by the simple object in this multifusion category. And this can be understood in the following way. We can just insert the loop and inside this, and then we take the street calculus, and for each edge, then we remove all this part, and we will get back to the original lattice. Then we'll define a corresponding metric. And the model is just completely the same as the Levin streaming model. We will have the vertex operator and the phase operator defined in the following way. This is just the sum over the BFT, and the omega k is just what I write here. And for this YK, I would like to stress that this YK is local normalization factor. This factor can be chosen freely, and the other the restriction of some consistency conditions. Here we just take the irrespective form. It's just the dimension dk. For the multifusion streaming model, its topological excitation is just the duplicate of this multifusion pattern. And now the basic question for this model is that what is the charge symmetry and what is the gauge symmetry and the charge symmetry? The gauge symmetry should be a root copy algebra. The charge symmetry is also root copy algebra. The charge symmetry must be a quasi-triangular root copy algebra, because that's the outer face is a unitary modular tensor category. So there must be some gradient structure behind this charge symmetry. And the boundary symmetry is just the topological algebra. This this can be understood in the following way. Because given a topological algebra A, we know that we have the category involves all the A modules. This A modules is just the category over the module category over the given unitary multifusion category. So basically, this is the correspondence. So we can understand that for the gap boundary of the unitary multifusion category, its gauge symmetry is this W comodular algebra. But the charge symmetry, as we will explain later, it's given by the two algebra. So now let us construct. Let us now explain how to construct this we call algebra. And we find that for the bulk phase, we can actually let us just consider the following configuration. If there is some excitation for a given region, then we can divide this region with the region with low excitations. There is the orange region. This orange region, we can find that it's just some closed loop with some layers. And if we can do some local moves, if we do the local moves, eventually we'll overtake the simplest configuration. This is just like a tube. If we just take this as a tube, then we'll have the right side figures. Then we can consider this configuration. This configuration is the basic configuration for the boundary tube LV. If we're just using this configuration and we span a space, and this is called the tube algebra. This tube algebra, we need to show that this is root copy algebra, and this can be shown in the following way. And we can do it with unit structure. This unit morphism is defined in the following way. This can be regarded as identity map, because this is this dashed line is just the tensor unit, so it can be regarded as identity morphism. And the multiplication can be defined very intuitive. I mean that we know that for two tubes, we can just take the gluing of these two tubes, then we take a new tube. For this process, we can just take the inner product, because this action is on the right hand side, so we can just fuse them together, and we can just multiply them together. Then we take the local move. for the right hand side to recover the original configuration. This can be done, because we can just take the F loop over this upper side and this lower side. Then we take the loop move, and we can remove the loops, and they will recover. They will come back to the original configuration. So we can define the algebra, and we can show that this is an algebra structure. And the co-unit is divided in the following way. It's like for the intuitively, it's just like we take for this tube, we close the both sides of this tube, the left hand side and the right hand side. We close them, and they will have a co-unit structure. This is just the co-unit. For the co-multiplication, is a little bit complicated. We also have an intuitive understanding. For the middle part, for this middle part of this tube, for the back side and this front side, we just shrink them, and we cancel them, and we will make them into the two tubes. These two tubes can be understood in the following way. This is like we can insert the line, insert the line in between this E and F, and then we take the local move, and we cut this this graph into two graphs, and we'll have the corresponding co-multiplication structure. And we can show that this is a co-algebra. And it can also be shown that this co-algebra structure and the algebra structure are compatible with each other. They can form the weak bi-algebra structure. And there is an intuitive way to understand why this is a bi-algebra structure. Because we know that for the weak bi-algebra, because we know that for the bi-algebra, if we take the co-multiplication, this must be delta over this one must be one tensor product one. But if we take this co-multiplication, we'll see that it's just a weak Hopf algebra. This is best motivation for us to do this. And this is inspired by the Kitaev and Hopf's original work for boundary theory. And we can also provide the adpole operation in the following way. This is like we can just drag the lower part into the top part, and we take some moves, and we can divide the following way. And there is also a star operation. A star operation can be divided in the following way. And we can show that this Hopf algebra is a C star weak Hopf algebra. And now to argue that this gives the weak Hopf algebra, we need to argue that its representation category is just matching with the topological face of this streaming model. There is a basic way that we can argue this. This is very similar like the Kitaev work. And we know that for the boundary, because we have constructed this tube algebra by considering the bulk excitation as a defect over the trivial domain wall, which means that we regard T as the trivial domain wall to the TE phase. And the excitation is actually the functor category for this PD by modules over this D for this D. And for each D, we can construct a module. Actually, we can construct this VF or this upper or lower side, depending on the direction of this F. We construct the module. We can show that it's clear that there is some operation over the tube algebra, because we can just take the tube algebra over these spaces, and we just group them together, and there is some module structure. So this is the basic understanding of what is the topological excitation, why this tube algebra can be regarded as the charge symmetry of this bulk phase. And another interesting thing is that because we know that for the double model, there is some bottom double structure to this. So the next question for us is if we can just construct a bottom double model for this tube algebra. So we have the following observation. Because if we just take the vector charge on the right hand side, we can just embed the boundary tube into the bulk phase. And we can also do this in the right hand side. Then we take the cross product in the following way. It naturally gives us the tube algebra structure, the bulk tube algebra structure. So in some sense, it means that we have a boundary tube algebra, and we do some cross product with this boundary tube algebra. We obtain a bulk tube algebra. This bulk tube algebra, the replication category should be a unitary multiplication category. So there is some polytriangular structure, but we are still working on this. So so the basic observation is that the boundary tube algebra is just a weak Hopf algebra. It does not have a polytriangular structure. It's replicated category is just a fusion category or a multi-fusion category. And for the bulk phase, its cube algebra should be a polytriangular, we call algebra. And the boundary using the boundary bulk duality, we can regard the boundary cube algebra as the weak Hopf gauge symmetry. Weak Hopf gauge symmetry for the bulk phase. And for the bulk cube algebra, we can regard it as a charge symmetry. So this is the basic idea. And there's also a Morita theory for this weak Hopf algebra. Because as what I show here, that for this orange region, there are main lakes. So we just take the local moves to take this cube algebra. So the basic definition is that if we just come back to this original configuration, what is the relation between the original configuration and the simplified configuration? So they are related with each other by the Morita theory. Morita theory means that we have this n lake, we have main lakes, and we construct an algebra, and then we have two lakes. We have an algebra. They are represented category equivalent. So this can be shown that if we just take this configuration, this boundary configuration, boundary tube configuration, and the M0 equals to M1 and the N0 equals to N1, they form an algebra. And we can show that if they are not equal, I mean that if M1 is not equal to M0 and N0 not equal to the N1, they form a module, bimodule over the following structure. So this can be summarized as the following way. We have the Morita context in this sense, and we can show that the complicated structure, complicated configuration, and the simplest configuration are related with the Morita equivalence. So this is the basic results. And to make a summary, the cube algebra gives us the weak Hopf symmetry for the stringent model. Because we have worked this for the multifusion stringent model, this also covers the stringent model. So for the stringent model, we can also have this cube algebra. This cube algebra is just the weak Hopf charge symmetry. The bulk cube algebra is just the weak Hopf charge symmetry of the stringent model, and the boundary cube algebra is just the weak Hopf gauge symmetry for this bulk phase. And this can also be related with the quantum double model. And okay, so there are also some open questions. Because we have investigated this we call quantum double model and the multifusion stringent model. So the next question is that can we just generalize this into the higher dimension case? So and another one is that what is the entanglement property? I've not discussed this before, but for the we call quantum double model, we have the tensor network representation of this ground state. So it's natural to understand the entanglement property for this ground state. Because we have the tensor network structure, we calculate everything explicitly using the entanglement normalization. And for the third one is also if we have although we have just discussed we call quantum double model and the multifusion stringent model, their relation is not clear at this stage. We know that for the Hopf case, there is some precedence. We can just map quantum double model into the stringent model, but for the Hopf case, the problem is still open. And there is also some questions about the SCD or SCD generalization of this quantum double model and stringent model. And we're also working on the operator algebra perspective. So because we know that we have this quantum double model, this is a clear model, topological model. So can we just take the semi-dimensional elements using the operator algebra tools like the EF algebra? We take the EF algebra, we consider all the Weber operators and we discuss the states and its topology or other physical properties. Yeah, so I will stop here.
Okay, thanks for this great talk. Are there any questions or comments from the audience? Okay, let me ask you a question. So according to the general theory of n-equalization, a boundary can be determined by Lagrangian algebra, right? And according to the theorem, this Kitaev content double model, the boundary is determined by a modular algebra. What is their relation?
They're related for the Hopf case. We are sure that this is related by the smart product. Because we have actually we can just regard the boundary phase as some charge as some algebras representation category. So our target is specified with algebra, local algebra, that whose representation category is just this boundary phase. So for the general case, if you are asking what is the condensed algebra for this quantum double, we call quantum double boundary theory. I cannot. I think this is the open, still open. So for the general given, we call algebra. We have this representative category of this quantum double, and we can ask what is the complete theory, or can we give a classification theory of this condensed algebra over this in this category? I think that this is not solved. But for the finite group, there's a lot of imbalance.
Okay. Yeah. Any more questions?
不可模型是全部都是用代数的方式去算的。
我们用的是那个，就是我们定义的这个方式，就是我们定义的一个这样的 space， 然后是我们定义的对应的那个 operation， 我们去 check 逐一的 check 这个是不是满足它的那个会考那个这个 action。然后我们的这个核心的逻辑是呢，就是我们去验证它的 action， 发现它不满足所有的 action， 这是一个。它的 basic operation 实际上就是这个我们定义这个方法的 operation， 但是我们要做一些 local， 应该一些 symbol， 还有一些 local 的 symbol。
就是这一个 weight 的跟这个 Hopf 的最大差的这些验证的这个难点不在。
是 construct， 就是你要 construct 这个结构是不一样。对，你不知道这个要怎么去 construct， 所以这个难点就在你怎么去 construct，
在于怎么选择系数。
对。对，就是因为如果你给个 string 的话，你是没有什么直观去知道你去怎么去 construct 那个 Hopf algebra。你要去找这个 algebra， 你只能抽象去找。那这里的话就给了，如果在 string 上面的话，我们就可以有一个非常直观的方法去，因为这有一个 cube 的看法。如果我们用一个 cube 的看法的话，我们可以去尝试去有一个更加直观的方法去指导我们怎么去发现这个结果。对。实际上就是我们去 construct 的一个，我们在这个 boundary 的一个位置上面，我们去 define 这个 state。
就是一般是单位是单位是 Kitaev。
对。
你这个单位的话是可能分解成了一些手编码，因为无法，你这个出来是已经有那个，但是我不知道那个看不见。
就是这个 vacuum charge， 这个 vacuum charge 就是 depend on 你的 choice of EFB。就如果你这个 A 是从某个 sector 里面选的话，你这个对应这个 E 的话 ，identity 的话也是对这个 A 对应。如果 A 是从这个IG component 里面选，这里面的肯定是 I， 因为它不然的话，你选 B 的话，它是不能 fuse 这个东西，它就必须是你这个 fuse 的话，这个线的话是由你的这个 vacuum charge 决定。对。
我总觉得这应该是有想法。
但是这个对 fusion category 是没有问题，但是如果是 multifusion 的话，这个是由 A 的决定 ，A 本身决定的这个 case， 这两个线你选。那如果是 unitary category， 这个当然有问题，就是你这个就是 identity， 你 tensor identity。
我看你们最后还要做分数。
对，
是这么说。
就是我们有些基本的想法，就是对boundary theory 的话，你boundary defect 是结构是比较清楚。所以还是用，如果是你boundary结构比较清楚，我们去个 Hopf， 然后这个 Hopf 可以做到一个 EF algebra， 然后我们就可以去尝试用那个算赛数的方法。因为我们 local operator 是给定的，是非常 key。对，然后我们就可以去对 local operator 那个stabilize 肯定是做限制，然后去 define 这个 ground state， 然后 ground state define 出来之后，我们就找对应的那个 GNS 的 GNS representation，and 在一个 GNS representation 里面找到它对应的一个 state，这个 state 就是一个 superselection vector，然后可以把这个 chart 估算出，帮这个 chart 估算。
我有个就是那个在那个 model 最开始它的那个 input 应该是一个 fusion type 一个 fusion type，它的 output 是一个 UMTC。然后如果你现在把它 input 换成 multifusion type，那它 output 仍然是 UMTC。
是的，这个数学上来看是这样，但是如果你要从物理上去证明它的话，你得去构造相应的那个需要 vector 去 check 这个是不是它确实这样。但是你如果从数学看的话，你一个 multifusion type 这个 vector still 是一个 UMTC。对，就是它，并且这里面有一个直接就是你一个你给定一个 multifusion type， 我们知道它是对等的那个，它是 DIG， 它这个 DII 这个 component 永远是一个 UFC。那它的这个 general center 就永远等价于它的 DRI， 所有 DRI 的那个 general center， 这个也很重要。这个我没有讲，但是这个就是这个可以拿来做什么东西？这个可以拿来做 defect 的内容。我们内容它不是有些可能因为这 defect 报 defect， 我们可以 multifusion symmetry， 我觉得有一个比较重要的价值就是所有的 defect 的那种 model， 我都可以去把它嵌入到一个 multifusion 里面去。它的 defect 是被不同的 set 来 defect， 比如说我们的这个 bug 有一个 set， 大概是 component 里面的，另一个面就大概什么，这个 domain wall 它就是被看成我 data 的线索，所以它是不算。
So if no more question, and let's thank the speaker again.